Another way to estimate the center 95% of a bootstrap distribution is, instead of using the 95% rule with standard error, just calculating the percentiles in a more straightforward fashion. So the center 95% should be between the 2.5th percentile and the 97.5th percentile. We could think of it that way, but it's easier to think of it as being having 95% of the dots in the center of the distribution with 2.5% in each tail. So in this image here, we have a total of 1,000 bootstrap samples. We have 2.5% of that 1,000 in each tail. So if we wanted to estimate these endpoint values by hand, then we would want to figure out how many dots are in each tail. So if we have a 95% confidence interval, that means that 5% is going to be in the two tails combined. In this case, 5% of 1,000 samples is 50. So that tells us that we should have 25 in each tail. Now we can count them and verify that that's correct. Maybe I'll choose a color other than red. We've got 1, 2, 3, 4, 5. Now it gets a little bit harder. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So we can see that that is in fact 25 dots total in this tail. And then we could count the dots on the other side as well and verify. Feel free to do that yourself. These dots end right in the middle of a bar, but we can tell which ones are red and which ones are black. Hopefully on your printout, if it's black and white, they may appear as a slightly lighter shade of gray. But we have 25 dots on each side. Then what we would do is try to estimate the value of this endpoint. And we can tell without looking at the number marked here that is close to 0.94. We can tell that this one is close to 0.88. From there we would, if we were doing this by hand, just try to estimate the value. But in this case, the confidence interval goes from 0.875 to 0.943. And if we look at that compared to the one that we found by calculating a margin of error, that one was 0.878 to 0.95. We can tell that they are pretty close. They're not exactly the same, so it is close, but we can also observe that we had a little bit of left skew in this graph, and the one that comes from the graph is just inched a little bit to the left of the one that we found using standard error. And that's no surprise. If we had to answer as to which one is better, we would want to say this one's better. The one from Percentiles is more reliable than the one that just uses that rough 95% rule. So this is generally considered more reliable because it does not rely on the shape of the graph being bell-shaped. The percentiles method is still valid for any shape graph as long as you don't have all of your dots just stacked up in a few bars, in which case it becomes very hard to tell where in that bar is the breakpoint. We don't really need to be concerned about those special cases though, because they don't come up very often, and when they do come up, it's usually for a less commonly used statistic like a median instead of a mean, for example. It does sometimes happen with proportions, that there's just a few values that the Bootstrap process can generate, and it just keeps generating those same values again. That does make it a little bit harder to find a confidence interval. In any case, the percentiles method doesn't really rely on the shape of the distribution because it is supposed to still represent the sampling distribution, and we are still able to find bounds for that center 95%. Now, if we go to this graph in StatKey, and from this distribution we already have, if we just click on two-tail, we get a graph that looks like what we were just looking at. And now I touch this 0.95 and I change it to 0.90, or even just 0.9, same thing. I can see that now I have the center 90%, and I have 5% in each tail, adding up to 10% total in the tails. This gets me an interval, in my case, from 0.882 to 0.941. Of course, yours might be a little bit different from mine. So this gets me 0.882 to 0.941, and you might already guess that what this really is a 90% confidence interval. So we can start to change the confidence level now that we have this percentiles method. And is it wider or narrower than the original? Well, looking back at this graph again, when we had 10% in each tail, in the two tails combined, instead of 5% in the two tails combined, it does look like it got narrower. So, something very important to get your mind around intuitively about confidence intervals is that lowering the confidence level gets you closer to a precise estimate. It actually gives you a narrower confidence interval. And that idea is clear if we think about our Garfield comic, right? The 100% confidence interval was the one that was so wide as to be completely useless. As you start lowering that confidence level away from 100% and start allowing for your interval to maybe be wrong a little bit more often, you do get a more precise estimate. But that goes contrary to what first guesses often are. So let's look at this summary down here and see if we can guess the answers to this. Well, of course, since you're just watching a video, I guess I will be filling in the answers, but you can try to guess them as you go. Maybe pause this right now and think about them for a moment and see if you're able to guess which ones will result in a confidence interval that is more narrow. We've already said that decreasing the confidence level gets you a narrower confidence interval. So I will say that decreasing the confidence level to 80% would achieve this. Increasing it to 99% would make my interval get wider, a little bit closer to the Garfield one, right? We're getting close to 100% confidence. All that means we don't get any more data, we don't get any more information. It just means that we have to be that much more certain that we're not going to be wrong, which means we have to let our interval get wider to accommodate our uncertainty. Generating more Bootstrap samples from the existing data generally just makes it converge, right? It makes the graph better, and it makes the graph more reliable, but it does not bring in any trends like a wider or a narrower confidence interval. It might jump around a little bit as you're generating more samples, but then it will start to converge, and as you get more samples, once you've started to converge, you shouldn't really see any changes at all. So this does not make the confidence interval more narrow. But gathering more marriage licenses for a larger sample does make the confidence interval more narrow. If we think back to the flipping a coin example that we looked at when we first brought up the concept of confidence intervals, recall that what we saw here is that our estimate of the probability of flipping a head got better as we got more data, right? We had a really wide confidence interval when we were only looking at the first 20 flips, but we got a much narrower confidence interval if we allowed ourselves to look at the first 100 flips. So getting more data does get you a more narrow confidence interval. As n increases, your margin of error decreases.